Today's episode dives into three striking advances, pushing AI in very different but equally exciting directions. We'll explore a systems breakthrough that makes multimodal LLM training faster and more memory efficient at massive scale, a clever layer swap method that narrows the multilingual reasoning gap without retraining from scratch, and a new self-trained verification framework that helps models critique, refine, and improve their own reasoning. Together, these papers reveal how AI is evolving across infrastructure, language, and reasoning itself. Let's explore the first paper, Big Mac breaking the Pareto frontier of compute and memory in multimodal LLM training. Big Mac introduces a dependency-safe nested pipeline for multimodal LLM training that breaks the usual trade-off between throughput and activation memory. Existing compute-efficient systems, such as Optimus decouple the encoder and generator from the LLM pipeline, but this forces retention of encoder activations across the full pipeline and can also Zaderjlo LLM activations until generation completes. Memory-efficient systems such as Megatron Distrain integrate all modules into one pipeline, but then model and data heterogeneity create bubbles and stall the slowest stage. Big Mac keeps the user-specified LLM schedule, including interleaved 1F1B and nests encoder and generator microbatch units only at dependency-safe points. So the encoder and generator each require only O1 activation memory, while the LLM backbone remains unchanged. It also replaces rigid FSDP all-gather with a one-sided NVSHMEM poll to remove synchronization barriers and supports distinct context parallel groups for encoder and LLM. On a 128 GPU Hopper cluster, Big Mac speeds up MLLM understanding with Qwen 330BA 3B plus a 1, 3BVY by 1.08 times, 1.9 times over the baselines, and MLLM generation with the same backbone plus a 20B MMDIT by 1.5 times, 1.9 times, while keeping peak memory flat as batch size increases and avoiding the out-of-memory failures seen in Optimus. In production on a 345B parameter MLLM across 1,536 Hopper GPUs and more than 18K iterations, it preserved stable loss dynamics, with average loss deviation below 10, -3 versus Megatron LM in controlled tests. Let's explore the second paper, Rethinking the Multilingual Reasoning Gap with Layer Swap. Rethinking the Multilingual Reasoning Gap with Layer Swap argues that the apparent multilingual reasoning deficit in long chain of thought LLMs is much smaller than previously reported when native language and English pivoted specialists are trained under matched supervision. Using Qwen 3 8B base, the authors build a 32K context multilingual reasoning corpus of roughly 500K samples per language across English, French, German, Spanish, Chinese, and Swahili, translated from Dotsi Think SFT 32B with component-wise chunking to preserve reasoning traces. After supervised fine-tuning at about 10 B tokens per language, the native vs English pivoted accuracy gap on MGSM Rev 2, Global MMLU Lite, GPQA Diamond, M24/25, and HumanEvol Plus falls to 1.9%, 3.5% on average, with most of the remaining deficit concentrated in AMI 24/25. The key novelty is a weight space analysis showing that language-specific fine-tuning updates are strongly aligned in the middle transformer blocks, especially layers 1322, while diverging in early and late layers, suggesting a language-agnostic reasoning core surrounded by language-specific input and output processing. Exploiting this, the paper introduces layer swap, a training-free model merging method that replaces the native specialist's mid-stack layers with the English specialist's corresponding layers. This preserves nearly 100% target language chain of thought fidelity while closing 83%, 89% of the gap in French and German, 60% in Swahili, 27% in Chinese, and fully matching the English pivoted ceiling in Spanish. The method improves average accuracy on the target language evaluation set, for example, from 72.36% to 74.74% in French, and from 66.98% to 69.09% in Swahili, without switching the reasoning trace back to English. Let's explore the third paper, Self-Trained Verification for Training and Test Time Self-Improvement. Self-Trained Verification, STV, addresses a specific bottleneck in reasoning model self-improvement. Verifiers can judge final answers, but they often cannot diagnose plausible wrong solutions well enough to drive refinement. The paper's key idea is to exploit a supervision asymmetry. When the same model is conditioned on the reference solution, it can usually identify the error. So STV distills this reference condition teacher verifier into an unconditioned student using on-policy distillation with an alpha divergence objective at alpha equals 0.5 plus an RL term for verdict accuracy. Using Quinn 3, 8B on hard DAPO math problems and Sino Eval science tasks, STV roughly doubles final round pass at 1 on hard math, and on the hardest scientific reasoning split, it jumps from 1.5% without verification to 21%, outperforming much larger Quen 3 32B and Quen 3 235B A22B baselines. The trained verifier also scales better across 2, 0, plus refinement rounds and shows 3-5 times higher precision at matched coverage, reducing reward hacking. The second contribution is verifier in the loop training. After standard RL from verifiable reward has converged, the generator is trained inside the VR loop against a frozen STV verifier, yielding a further 33% gain in final round pass at 1 and a 30% relative gain in standalone pass at 1 with no verifier at inference. This shows that better verification can improve both test time refinement and training time generator capability. That's a wrap on today's AI paper highlights. Thanks for watching.